So in question 13, we're given two different expressions that are just monomials, right? There's no terms at all. You can see everything is just a collection of factors that are being multiplied together. And we're asked to rewrite these expressions without the use of parentheses or negative exponents. So two things I think I want to review is this idea if you have a power that's raised to a power, how do we deal with that? And if you have a power, if you have two powers that are multiplied together and have the same basis, how you can proceed with that. So in this top one here, I've got a raised to the b raised to the c power. And if we were to just think about this, right, we could have, for example, 3 raised to the second power, and then I could raise that to the fourth power. Now what this says is that I have exactly 4 collections of factors that look exactly like this, right? I've got 4 of those 3 squareds. And if I wanted to, I could rewrite this as 3 squared, there's 1 of them, 2 of them, 3 of them, and finally 4 of them. So I have 4 collections of the 3 squares. And each one of those contains 2 factors of 3, right? This is 3, 3, 3, 3, 3, 3, 3, 3. So if I were to expand it further, I would say I've got 2 factors of 3, 2 additional factors of 3, 2 more factors of 3, and then finally 2 more factors of 3. So all of these factors of 3, I can just count up and decide, you know what, I don't have to write this out in this expanded form like this. They're just 3s. In fact, I've got 1, 2, 3, 4, 5, 6, 7, 8 of them. So I can rewrite this as simply 3 raised to the 8th power. And you can see this is exactly what we're told we can do when we look at this exponent rule, right? It says if you're raising a power to a power, you can go ahead and just multiply the inner power, that's the b, times the one outside the parentheses, the c. So if I was to look at this original problem, it's saying, hey, you can just multiply the 2 times 4, and when you do, you get the 8. It's a terrible looking 8. You get the 8. So that's one rule for exponent that we can use, and it's nothing crazy other than just understanding what an exponent is and then expanding it and just thinking through, well, what does that have to be? The other one, it says if you've got identical bases, so for example, if I've got 3 squared and I multiply that by 3 to the, I'll go to the 5th power, right? This first thing says that I have 2 factors of 3. In fact, I can write that part out as 3 times 3. The next part says that, well, here you've got 5 factors of 3, and you can expand that as well. That's 1, 2, 3, 4, 5 factors of 3. Now, I am multiplying these factors of 3 together, and when I do that and I count, I see that there's 1, 2, 3, 4, 5, 6, 7 of them. So this can be written as, it's all 3s, that's all I have, and I have 7 factors of 3. And again, you can see, oh, because the bases were the same, I could do that, and instead of going through and writing this out like this now forever, what we can do is just say, look, we're going to take this 2, and we're going to add to it this 5, and we're going to end up with the fact that there's 7 of those. So this is 3 raised to the 7th power. So let's take a look at that and see how we can apply that to these two problems. So our first one has something raised to the 8th power and something raised to the negative 6th power. Now we've dealt with our friend negative 6 before, but right now we're just going to go ahead and use this power to a power rule and rewrite this. So I'm going to rewrite it starting with, hey, I could write all this out, but I know that once I collect it at the end, I'm going to have exactly 8 factors of 5. So it'll be 5, 5, 5, 5, 5, 5, 5, 5 written all over the place. But I could just go ahead and jump to this and say, that's 5 to the 8th power times a to the negative 16th power times b, 3 times 8 is 24th power. Now let's just keep doing this, times, the next part is going to be 5 raised to the negative 6th power and then I'm going to multiply that times a to the negative 6th power, and then finally I'm going to multiply that times b to the positive 12th power. Now, when I look at it, I can see I have several different bases that are the same, and we want to think about them together. So I want to think about my base of 5. You can see I've got 5 to the 8th, and I've got a 5 to the negative 6th. I want to think about my base a. I've got a to the negative 16th, and I've also got a to the negative 6th. And I also want to think about this b to the 24th, and b to the 12th power. So dealing with the 5s, right, I can rewrite this as 5 to the 8 plus negative 6, right, so I'm just adding those exponents, which is just simply 5 squared times. Let's do the same thing for our a's. I've got a to the negative 16th and a to the 12th, or I'm sorry, a to the negative 16th and a to the negative 6th, which is going to give me a to the negative 22nd power. And then in terms of b, I've got b to the 24th and b to the 12th, which would be b to the 36th power. And you can see all these pieces, right? Here's my bases of 5, so are all collected together now. My bases of a are collected together now. And my base with b is all collected together now. So there's one more thing that we should take care of here, and that's the negative exponent, right? So I can't say I'm done yet, but the way that we typically think about dealing with negative exponents is we always have this understanding that anytime I have an expression, I can totally multiply that by the number 1. And it turns out if I multiply this by the number 1 in the form of a to the 22nd power over a to the 22nd power, this does something wonderful for me. And again, my problem was the fact that I'm dealing with this negative 22nd power here. Well, when I've got a to the negative 22nd power times a to the 22nd power, and I add those, right, that would become a to the 0 power. And a to the 0 power, as anything raised to the 0 power, it turns up being just the number 1. So what that does for me is it allows me to get rid of the a to the negative 22nd power, and it ends up putting 22 factors of a in my denominator. So we can rewrite this a step further. I can write it as 5 squared times b to the 36th power all over a to the positive 22nd power. And it's fine if you leave your answer like this, but it's also okay if you go ahead and rewrite the 5 as 25. Either way is fine. So we'll leave this one here. Whoops. We'll say our answer is 5 squared times b to the 36th over a to the 22nd power. So let's turn our attention to the second part. And I think one of the things we could do first, if we wanted to, is we could get rid of the negative exponents, I think, at the beginning. If you wanted to save that to the end, that's okay. But if I wanted to get rid of this x to the negative 5th, I could multiply the numerator and the denominator by x to the 5th. And if I wanted to get rid of the y to the negative 3rd that I see in the denominator, I can multiply both the numerator and the denominator by y to the 3rd power. And again, my motivation here is by picking x to the 5th, we'll neutralize this. And multiplying by a giant one in the form of y cubed over y cubed will neutralize this negative exponent. So let's go ahead and write where we're at now if we make those two, if we multiply by those two values. I believe we end up with 15. I didn't like that. 15 in my numerator, y to the 5th. And then my denominator, I've got a 3x squared, and I'm going to square that, and I'm multiplying that now by x to the 5th. Okay, so my negative exponents are gone. for now. Let's go ahead and deal with this 3x squared squared. So there's two of those, right? So it's going to be a 3 squared, which is 9, and x squared, which is x to the fourth. So in my numerator, I've got 15y to the fifth. In the denominator, I have 9x to the fourth times x to the fifth power. And those can be combined. So we might say that we are now at 15y to the fifth over a 9x to the ninth. And then there's one more thing we might want to do. I know that's y, but if we look at 15 ninths, right? 15 is the same thing as 3 times 5, and 9 is the same thing as 3 times 3. So there is this common factor of 3, right, that forms a giant 1, and we can remove that from the problem. So I guess in our final simplified form, I would probably write the numerator has got a 5y to the fifth power, and my denominator, we're left with 3x to the ninth power. So we'll leave it there. I hope you found this helpful.